Oh, yeah, I've got, okay. Yeah, so I can't stop myself from giving you a very basic slide. This is a many body Hamiltonian, which can be written in two parts, non-interacting and interacting. So the basic question is, of course, the most basic question, how these subunits interact with each other. I want to ask about the quantum correlation about subunits. Quantum correlations, the moment I talk about, it becomes entanglement. So naturally, when we talk about quantum system, the first thing is to find out the state of the Hamiltonian. If you want to ask about the entanglement between subunits, you should choose the appropriate Hilbert space. That is the Hilbert space of the non-interacting Hamiltonian. So this is the idea. So what is the existing questions, what people want to study? The growth of entanglement, because different subunits are interacting with each other, but that interaction is not constant in time. That will develop in time. And naturally, the number of ways subunits can interact with each other can be more than the number of ways they cannot interact. So entanglement grows in time. This growth is of interest for various reasons. Okay. And of course, one fundamental reason is that what is the time limit after which quantum information cannot be retrieved from the dynamics? Not because entanglement is not growing, it is just because of our own ability that we cannot perform that kind of experiments or measurements. So basically, ultimately necessary to understand the dynamics of entanglement due to changing system conditions over time. The particular questions I'm interested in, role of physical constraints on the entanglement, basically growth of entanglement under changing system conditions. Is it sufficient to know the average value of the entanglement measures? Because you cannot exactly calculate, you are talking about the many body systems. So you have to talk about the, these entanglement measures are fluctuating. So you have to talk about their distribution. Is it sufficient to calculate the average value, or you also have to take into account the fluctuations? And then, of course, the most important is starting from a state with arbitrary entanglement, can you control the variation of the parameters to reach the maximally entangled state? Okay. So I will, for the purpose of this talk, I'll take a very simple case, pure state, bipartite system. So my system consists of two subsystems, A and B, and they have their local Hilbert space. Local Hilbert space of A is given by AI states, and local Hilbert space of B is given by BJ. Okay. So naturally, product basis, if you're writing the state of the total system A plus B, it can be written in this form. The form is, this is gone. Okay. Yeah, no, where did I go? Oh, you have seen my whole talk. I can leave now. Yeah, here. Okay. Yeah, so basically the point is that all that if you have written your state in the product basis, all that you have to focus is on this coefficient, on these coefficients Cij, because in the bipartite state, the coefficients have two indices. So you can collect all these coefficients in form of a matrix. And basically this matrix you have to study for all properties of the quantum system if you are interested in the state. Of course, different state of the system will have different coefficient matrix. I call this matrix a state matrix. Okay. Now, so if you want to study the entanglement measure of a bipartite system, you have to consider the Von-Neumann entropy, R1, which is defined like this. Here, rho A is the reduced density matrix. You can also study Rayleigh entropy, which are many of them, but here I'm just writing R2, the second Rayleigh entropy, which is given in this form. So basically, all that you need to determine is the reduced density matrix. Reduced density matrix is calculated from the density matrix. For a pure state, density matrix is given like this. Reduced density matrix is obtained by partial tracing of the leftover system of the density matrix. So here leftover system is B. So you trace over B and get the reduced density matrix of A. So you see all other details are immaterial. What matters is that the reduced density matrix comes out to be of the form of CC dagger. So again, all that you need to know is the details of C matrix. Okay, So if you know the details of the C matrix, by using this formula, you can calculate the your Von-Neumann entropy, Rayleigh entropy, and that is sufficient for bipartite entanglement. Okay, question is now, as you understand now, the question is, can you determine C matrix for a many body system? Okay, so so naturally you start with a very simple case. Simple cases, a typical state is ergodic. So Michael Berry came up with this idea in context of quantum chaotic systems. Essentially states that the energy eigenfunctions of quantum chaotic systems behave as if they were Gaussian random variable. Mark Schrednicki further elaborated it in context of many body systems. A typical ergodic many body eigenstate constitutes a random Fock space vector with independently distributed Gaussian entries. What it amounts to say is that the C matrix, the matrix elements of C matrix can be treated as independent, identically distributed Gaussian variable. So this is it. So basically what it is saying, you do not know exact knowledge of the coefficient, these components Cij, but you just treat them as Gaussian random variable. Why don't you know exact variable? Because it's a many body solution, many body Hamiltonian. You try to solve the exact state. If you can solve, it's very good, but I can promise you, you will not be able to solve for many cases. Okay, so question is, so if you cannot solve, so Cij has a distribution. If Cij has a distribution, so therefore your entanglement measures have a distribution, and you have to study the distribution of C matrix, and that will lead you to the distribution of entropies, entanglement measures. So this is the case. You have, what can you say from here? The distribution of entanglement entropies. So first you study this. This is a case for ergodic state. But
entanglement measures are sort of some moments of the distribution. They are not. The entanglement measures are moments of distribution. They are not. They don't have a distribution of measures, right?
Moment of distribution of what?
Some eigenvalues.
No, it depends. That's what my okay. Let me ask. I said that the Von-Neumann entropy depends on the reduced density matrix. Reduced density matrix depends on C. If C itself has a distribution, then the any measure which depends on the distribution of C will have a distribution. You cannot calculate it. That's another matter. But it will have a distribution. If C itself has a distribution, let me just go back to the formula. You just substitute rho A there.
So C has a distribution, but R1 doesn't have a distribution.
Why?
R1 is just a number.
No, wait. R1 depends on the summation over eigenvalues of rho A. And if eigenvalues are fluctuating.
Okay, I beg your pardon. Okay, I understand. It
allowed.
is not the average over R1 is not being taken yet.
So okay. So Satya has already done this case, the totally ergodic state. So I'm not interested in this. So before I finish my time, let me just at least mention what is mine. So non-ergodicity is typical. Okay. A typical many body state need not be ergodic. Not all components Cij are of the same order. By the way, this work I'm going to present is highly technical. If I can reach to my main message, that will be sufficient for me. Okay, so the question is how to determine state matrix, because as I already said, if you can determine state matrix, you know how to calculate the rest. Lack of detailed information about the many body interactions, or even if you have exact information about all the interactions, your own incapacity of calculating the matrix elements in the given suitable basis makes the Hamiltonian random matrix. But of course, it will be a system dependent random matrix. It will not be the standard random matrix which people usually talk about. System dependent random matrix means it will be sparse, banded. Different matrix elements will have different parametric distributions. So randomization of the Hamiltonian is expected to manifest in typical state of the system also. Some or all eigenfunctions components of a typical state can be random. Okay, this is the slide done by my, oh my God. Okay, this is a slide done by my student. So it is just to convince you, this is a random field Heisenberg model. and this is the ground state. He is trying to show here the distribution over the ensemble of a particular component of the ground state. So in the ground state, look, this is one component over the ensemble. This is another. Ensemble is created by the disordered. It's a disordered by changing the disorder. So this is the one component of the ground state. This is another, and you see. But if you go to the excited state, the distribution is very different of various components. This is just to tell you that depending on which state you are, the distribution of components can be very different. So therefore, if you want to calculate the entanglement entropy of a many body system, the moment you change, you have to again study the whole thing all over again. Question is there a way out? Okay, so there are two possibilities. One way is you write down the system-dependent random matrix ensemble of your Hamiltonian and calculate the eigenfunctions and do the analysis. Other is you directly go to the eigenfunctions, write down its state matrix based on the available constraints, use the maximum entropy hypothesis and do the calculation. And that's what I'll talk here. Okay. The type of constraints can be matrix constraints, which are global constraints depending on symmetry or conservation laws on the system. And then there are local disorders, what kind of interactions you are, which part has randomness, which part does not have randomness. So those will reflect on the ensemble distribution, ensemble parameters. Okay. So for example, quickly, here suppose this side is the subsystem A, this side is subsystem B. Assume that if all these basis states of A are interacting same way with B, so all of these correlations are of the same order. But you can also consider different situation when only first of them is interacting in one way, the all others are differently. Various possibilities are there depending on what kind of eigenfunction dynamics you have in your local Hilbert spaces. Okay, so what will be the corresponding C matrix is in the next slide. So if you have all basis states of both the subsystems interacting with each other in the same way, so you will have the C matrix uniformly identically distributed. In the other case, you will have a different kind of matrix elements. For example, here color coding tells you whether the matrix elements are of the same order or not. So here, and I try to use the spectrum. My student doesn't like this kind of choice, but I like these colors. So that's why I've chosen. So basically this means their color, here the strength is very different from here. Similarly, here strength of various are much more different. So question is, and this can be one state of the same system, this can be the another state of the same system. The moment you change the state of the same system, you have to do the analysis again. Question is, can you do it? No. Okay. So basically, I'm now going to ask, of course, because as I've already tried to motivate you that you have to look at the distribution of the matrix elements of the state matrix in a many body system, you don't have much alternative. Okay, so if you have to look at that, then you basically, this is a distribution, general distribution, but of course, nobody works on general distribution. So let us look at the simple case. Simple case, the next level, not ergodic, but next level to ergodic. Okay, so that means if you allow the ensemble, if you know the ensemble constraints on the first and second order moments of matrix elements, then you come up with this kind of Gaussian distribution. But this Gaussian distribution is very different from the ergodic state because here you have different mean values and different variances. Of course, you will say there are 2n square parameters here and this is impossible. And you ask Satya and he'll tell you, yes, it is impossible. But just a few days ago, I was trying to convince him that he should look at my paper and I can do it. Okay, the answer is this, that you can find a single parameter, it seems, of course, it is very technical now, to that you vary these parameters, HKL and BKL. These are ensemble parameters, but these parameters contain information about the system conditions. So you vary these system conditions. So these parameters vary, but the dynamics of the distribution is governed only by a single functional of all these parameters, not the evolution of the ensemble density of C matrix does not know about the details. So this parameter I call complexity parameter, and Okay, let me see what is. So once you know, so this is basically the distribution of your Von-Neumann entropy. Okay, so now you can calculate, and once you know, you can write down. So this was a diffusion equation you obtained for the state matrix, because once you can calculate the evolution equation for the ensemble density, you can calculate from there the evolution equation for Von-Neumann entropy, distribution of Von-Neumann entropy. Okay, and I'll not bother you now because I have just few minutes now. Let me just go back to, so if you are interested in the average, from here you can also calculate, because once you know the distribution of Von-Neumann entropy in terms of parameter y, you can calculate the average by the standard formula. I have forgotten here to put, okay. And then you can solve that equation, and here is the result. And we have done it for the both the Von-Neumann entropy and the Rayleigh entropy. The average value, we have also done the distribution, and it turns out to be in terms of the complexity parameter for, yeah, okay, sorry, I should have said. So for 3 different ensembles, they represent 3 different states. 3 different states. One is, this is uniform distribution. Here it is a variances distribution power law wise. Here it is variances changing exponentially. When I say ensembles variances are changing, that means underlying system conditions are changing. So they may represent the 3 different states of the same system. They may represent 3 different states of different systems. However, you see in terms of Von-Neumann, it is possible to study the evolution in terms of parameter y. The details here, all 3 of them are showing the same kind of evolution. Here you see. So it is with respect to parameter y. Now let me just quickly come back. I don't want to stay, okay. Yeah, this is my last slide. So what I have tried to tell you in 20 minutes is a typical non-ergodic many-body state represented by multiparametric Hart ensemble. If you allow me that, then it is possible to study the entanglement measures in terms of a functional of all these system parameters. And y has a, what I would like Satya to, say something about. Y has a form of an information theoretical function without bothering about the details. How I have derived. I just want to know, like, this is a logarithmic function. It contains the information about all the ensemble. So I call it some kind of information theoretical function. I don't know whether I'm right or not. So evolution of information entropies of many body states governed by an information theoretical function. And this is the last one to answer your question. No fluctuations are important of the entanglement measures. That is my conclusion. Thank you very much for your time.